Hello, everyone. Good morning, good afternoon, and good evening from where you are. Welcome to another Polkadot deep dive session. Before I start, let me introduce myself. I am Ayushman Mishra. I work in Parity as a Polkadot application engineer. This session will be presented by me, Garman, and Peter. And this is a continuation of our Ink and FASM contract series within the learning sessions. In this session, we'll be stepping into the advanced ink because in the last two sessions, we went through the smart contract and the basics about ink. So in the next slide, we'll go through the agenda. So basically, before moving here, in the agenda, basically first we'll do a recap of the smart contract and ink, and after that we'll do a deep dive into the storage and how we handle the cross contract calls. Then we'll explain the chain extension and how we can configure through the custom environment. At the end of the session, we'll do a deep dive demo. So let's proceed with the recap of palette contract and ink. So Substrate basically design palette contract in a way that it is decoupled from the language that is used to write a smart contract. This palette is only the execution environment and it takes WebAssembly files as input. So a smart contract for this palette have to be compiled to the WebAssembly target architecture. Any Substrate parachain can easily add a smart contract functionality by including this palette. If you want to know more, like how this contract palette works, I would recommend to please go through our previous sessions. Now, talking about Ink, Ink is an embedded domain-specific language for the Rust. This means that you can use all the normal Rust syntax plus some specifics that we added to make the language suitable for the smart contract world. The palette contract takes these ink contracts and executes them safely. So in short, with ink, you can write a smart contract in Rust from blockchains which are built in Substrate that includes the palette contract. Now I'm handing over to Gaman to provide some insights on the storage. Over to you, Gaman.
Before I start, I'll just give a little introduction about myself. My name is German. I work at Parity as a smart core, as a Rust core engineer. I work in Ink team. I joined Parity roughly 8 months ago from the Polkadot Blockchain Academy in Cambridge. Also happy to answer any questions with regard to that. And for my part, I'm going to talk about one of the I think most important aspects of smart contract development, which is storage. Even though it's a very theory-heavy concept and there's a lot to cover, I'll try to make this journey as smooth as possible. So on this slide, you can see the outline of the topics I'm going to cover in this section. So we're going to start with mapping, one of the core data structures in smart contract storage. Then we're going to move into storage layout. I'm going to explain how it's defined in Ink and how it might be different from the Solidity. Then we're going to move into custom storage items, specifically how you can define your own data structures and how you can store them in storage. And then finally, we're going to finish off with the generation of keys using automatic and manual methods. And finally, I'll just give, on the last slide, I'll give a couple of tips when consider when designing a smart contract storage. So let's start. We start with mapping, and you might have been introduced to mapping in the beginner session during the previous Polkadot deep dive with Ink. And in this part, I want to dive a little bit deeper and explain how mapping is defined in Ink and how you can use it. So there are a couple of properties to consider first. First point is the values are spread across multiple storage cells. What that implies is actually going to be explained later. That actually also implies that data is actually lazy loaded in the contract. This concept will also be explained in a later section. And what that means is whenever you access your data, whenever you try to access the data by the key, you only return the data under the given key. And finally, the point to consider is that the data that's returned from the mapping is actually a local copy. And in vast terms, it's you return an owned variable that you can interact with. So now let's look at the two snippets presented on the screen. On the right-hand side, you can basically see a very easy way how you can define mapping in your storage. So let's say we have some DAO example, and then we want to store a mapping of balances between account ID, which is address, and the balance. And you can do that as easy as just defining the field in your storage struct. But don't forget to add the import or qualify the mapping struct. Then on the left-hand side in the bottom, you can see how you can access the element and the given key and update it. So let's say we want to access the member balance, then you would do something like balances.get and then provide the key, which in our case is account ID. Then it will by default, it will return an optional type in case the value doesn't exist on the given key. For the simplicity of the example, we're just going to unwrap this value. Then we have a member balance. And then on the line 4, you can see that if we want to update the value, we need to insert the mapping back. So we insert the updated balance. So in this case, we want to just add some extra balance to the given entry. So in this case, we just do like something like member balance plus add, pass it by reference, and insert it under the given key. So moving on from that, we're gonna talk about storage layout. And before we talk about storage layouts, we need to discuss how data is generally stored in blockchain. And the blockchain data is stored in the form of tree with the keys and the values stored behind the keys. But for the simplicity of illustration, we're going to consider storage as a database with key value pairs, where the keys can be of arbitrary length, and values are encoded using scale encoded to sometimes optimize the storage and reduce reduce pair bytes and bits to optimize the storage. And there are two types of storage in Ink: pack types and non-pack types are the types that can be stored in Ink storage. And first, I'll start with boring definition, but it's very important to get the terminology right in order to understand the later concepts. And the pack types are the types whose values occupy a single storage cell. So now let's break this down and understand what this implies. So pack types essentially are certain types where all the values are stored under a single key. And one important fact about Ink storage is that Ink storage, like we define here, like the storage tract, is by default a pack type. So now let's look at the example. Suppose we now want to store in our DAO contract, we want to store a list of members in the vector in the list. For the sake that, for example, we might have a member in our DAO, but we may not necessarily have an associated mapping between the member address and its balance. And in this case, members is a pack type, and balances is not a pack type. And now let's actually break it down what this implies. So what happens here is with packed storage, if you want to access one of the fields, like now let's say like on line 5, we want to check the balances and check whether it contains contains the call address. When we do this operation on number 5, it will actually load the whole storage, including the list of the members from the vector. This also, like you can see on the illustration, that when we access a single value from our member list, from our member vector, it will not access the specific element from the vector, it will first load the whole vector into memory, and, uh, and then we'll do operation on it. So this is the implication of the pack types. Then let's now talk about non-pack types. Again, we start with boring definition. Non-pack types are the types whose values occupy multiple storage cells. So that means that with non-pack types, you can essentially have multiple keys, and each key will store individual values, and you can access this individual value by key. An example of non-packed value is mapping, because when you access an element at given key, you don't load all the other entries in the mapping. You just access the value on the given key, and essentially this is one of the biggest difference from pack types. And we can also say that the data from non-pack types, like from mapping, is loaded lazily. So that means you only access the data when it's requested. But in Ink, you can also decompose storage to be non-pack type by wrapping one of the fields into lazy. Then in this case, when you access one of the fields from storage, it will not load the field that's wrapped inside lazy. So now let's look at the example. So again, let's say our member list grows to insane length, and now it's too expensive to load it, and we actually realize that we don't load and access members that often. We can just wrap it in lazy, and in this case, when we want to access the owner or balances, we will not load members by default in memory. However, when we access the members, we will just load members from the storage. So now let's look at the example how you can do this in messages. So in this case, lazy by default now adds extra two methods, get and set. So now members is, if you remember from the previous slide, is of type lazy with some type, in this case vector, and we want to access the value underneath, like wrapped within lazy. So we call something like self-members.get, and this will return an option. So in case you haven't put the value inside lazy, then we just unwrap this lazy, and as shown like in one of the previous slides, we get one of the addresses at the given position. However, on line 9, we get owner message. If you just access the owner, you want to just read who's the owner of the DAO, then you do as simple as you do in Rust, you do self.owner, and in this case, the members list will not be loaded into memory. So now moving on to the next part, let's talk about how we can define custom storage types. And the question you might ask when working with Ink is, what if you want to define your own non-pack structure to be stored in contract storage? Well, to do that, your type needs to implement certain traits in order to make it storable. No problem with that. You can just derive the required traits like scale, decode, encode, type info, and storage layout. And now let's just, for the sake of example, let's say we want to have on-chain data about the member of our DAO. We want to store name as a string and email and potentially funds contributed to the DAO in order to calculate the rewards. Okay, yeah, we defined our member, but this is a little bit tedious and that's actually lots of code to write. And for this example, Ink has a better solution. We have a storage item micro attribute, which basically automatically derives all the necessary properties to make the member struct storable. The only difference is that in this case, storage item will also automatically calculate keys for any non-packed values within the member. But again, we're going to come back to keys in a later section. And now, let's say you want to define a generic struct, like uh, in this case, you still want to store name and email as strings, but you want to define your own type for storing funds. Like may not necessarily be a balance and can be just a raw U1 to 8 or U32. Again, no problem with that. You can define engineering, but as long as it implements packed and default, you can easily use it in your generic storage item. However, you need to be beware of Rust monomophization. So what that implies that whenever you provide the concrete type to a member, the Rust compiler will generate a concrete struct with member. It will replace the generic B with the concrete type that you provided. So that means that you're going to have as many definitions of member in the final generated bundle. You're going to have as many definitions of member as the number of generic arguments you used, which essentially can bloat the contract size, which is something you need to be aware and consider when using generic structs in your storage. Then now let's modify our DAO mapping example. And let's say for our owner, for our elected owner leader, we now want to store the on-chain data, like name, email, funds contributed. So all the members of DAO knows its leader or the owner. And yeah, now let's add another message to basically retrieve the number of funds contributed by the owner. Again, we can do as simple as just accessing the structs from the storage and accessing the given field. So now let's talk about keys. And this is one of the interesting and also theory-heavy concepts. And you can spend the whole session talking about keys, but I'll try to provide relatively in high level, but at the same time, well-explained overview of how to work with keys in Ink. So by default, every non-pack type in storage in Ink requires key to be calculated. By default, keys are automatically calculated by using the name of the field and the order of the fields in the struct. This is different. This is slightly different from Solidity, where only the order is taken into consideration to calculate the keys. However, when you do storage migration, or if you want to upgrade the contract and potentially change the field, this will mess up the keys in your storage. So if you want this extra persistence and guarantees of the key consistency, you can define your own manual keys. And for that, any types that you want to define manual keys for needs to be wrapped into lazy. And the reason for that, again, remember that this storage is by default is a pack type. So this doesn't make sense to have an accessible key for packed elements, because when you access the storage item, you access all the values automatically. But if you want to have dedicated key for each individual storage field, then you need to wrap each field into lazy. You can define a key. Mapping, again, by default is unpacked type, and mapping needs to have its own key in order to calculate its children elements with keys. And then for that, we have extra generic. You can define manual key, and then to show an example, you provide hexadecimal argument defining your concrete keys. So now coming back to the example, you might ask a question now, but that isn't member pack type, because we don't really have any fields, any non-packed fields. String, balance are all pack types, and this is actually correct. And we don't actually need to derive storage item for member if you're not going to use it if you're not going to use it as part of the storage item, let's say you want to store it in a list, uh, like a vector as a type, then in this case, you still need to derive all the types and all the traits in order to make it returnable by message and storable in vectors. That's because vectors and mappings can only store pack types. And storage item macro actually implies that the actual struct, the data type, is unpacked. So again, as explained on this slide, storage items are actually used for key calculation, because the keys needs to be calculated the compile time for all the unpacked types, because you want to access those individual items individually and load them lazily, like mapping and any types wrapped in lazy. So that's why storage item is very useful when you just want to remove this bearing of automatically calculating the keys. Um, but let's now slightly modify our member structure, and suppose we actually don't use email that much, and strings, you might remember that strings is essentially just a vector, an array of characters, and let's say our email can be insanely long and we don't want to access it all the time. And in this case, when we wrapped email, when we make email a lazy type, we actually turn member struct into non-pack type. So in this case, that implies that we cannot store it. We can no longer store it in vectors and mappings, and it absolutely makes sense to make it storage item. It can be also a case when you can have a mapping or another additional lazy fields in your member, and again, in this case, member is clearly a non-pack type, and it's beneficial to just use the storage item micro attribute to reduce the code. And finally, I just want to give a summary of what I mentioned earlier. So number one, coming back to mappings, just use mapping wherever it's possible. It's easy to use, memory efficient data structure that allows you to load data easily. Next point is pack types, is actually reduce the contract size, but they can potentially increase the gas cost. Like, as imagine you have structs with lots of vectors or large data, and whenever you access one of the fields from the storage, it essentially loads all the elements from your storage. And also, if the size during decoding, if the size of one of the storage items during decoding is above 16 kilobytes, it will actually break your contract. And non-pack types do the opposite. They can increase the contract size, and they actually provide additional read and write overhead. That's because, again, you need to go into database and look up specific key to access the specific value. However, it can also significantly reduce the gas cost if, again, you operate with relatively large data and complex data structures. So coming to piece of advice I would give from these 2 points is that you need to make a balanced and weighted decision about your storage layout. You need to carefully think about what kind of data will be coming in and coming out of your storage, and how much data is actually going to be stored. And based on that, you may want to just keep your storage simple and packed, or you may want to decompose your storage to be non-packed. Then number 4, use storage item for non-packed types. Again, if you define struct is packed, then you probably want to derive all the necessary traits to make it returnable by the messages and storable in lists if that's necessary. Number 5, generics. Indeed, one of the Rust features can definitely ease the development and reduce the line count, but it can increase the code size, and this is something you just need to be beware. It's a very nice and useful feature for development purposes and prototyping, But again, you need to weigh all the pros and cons for that. And number 6, use manual key if you plan for upgradability. Generally speaking, AutoKey the implementation for AutoKey generation hasn't been changed for a while, but it's quite possible that it's going to change in future. So again, if you need this extra peace of mind, I would advise to use manual keys. And this is the end of my part. I'm again happy to answer all the questions related to storage in Q&A. And now I'll pass to Peter to talk about cross contracts.
Thank you, German. Hey everyone, my name is Peter, and I've been with Parity for a little over a year now as a Polkadot application engineer. And I'm super excited today to talk to you about cross-contract calls, and then later in the presentation, I will be doing a demo. And cross-contract calls, the name, it kind of gives it away. What it does is you have a contract, and that contract will make calls to, to other contracts. And the first example of this is with contract references. And this is the first and kind of easiest to understand, where basically you actually have a reference to an already deployed contract. So on that first arrow there, the reference to deployed contract, for our constructor, for our adder contract, we are supplying a reference to an accumulator contract that we will then use in the rest of the contract. And to actually do this cross-contract call in this way is quite simple. Since we have it initialized with this accumulator reference, we can literally just call that field self.accumulator and then call the .increment function. And that .increment function is described in the accumulator contract. Now, one of the downsides to this way is you actually have to import the entire accumulator contract exactly as it is. So exactly the contract that is deployed on chain, you need to import that contract to your project. This just gives Inc enough information to actually make these calls. However, there is an easier way that was recently pulled into Inc, and this is with dynamic traits. And for dynamic traits, what you can do is all you need to provide is a trait. And then from that trait or that interface, you can then do these calls do a cross-contract call just with this interface. So for example, we have inside our storage, we have an Inc, and then we use a contract ref macro. And this basically initializes the trait to be called dynamically. And then you can see it in our constructor. We just pass in an account ID. And then with that account ID, Inc will kind of build the proper wrappers around it to actually use this in calls. And this account ID is the account ID to an already deployed contract or the incrementer contract that we will use. And just like before with the accumulator example, calling it once it's actually set up is super simple. You just call self.incrementer.increment, and that will actually increment it and do the cross-contract call for you. And this way, it's much cleaner than having to import your entire contract, because all you need to do is import the trait. So the box on the right is the trait. You just do the Inc trait definition macro, and then define the trait. And then you just use that trait in your contract, and you can do these cross-contract calls. Now, there is one more way as well, and this is the more complex and low-level way, but it is more advanced and has more flexibility. And this is with the call builder. And the call builder, like I said, it's more low-level, but it can be very useful to have more control over it. So in this example, it's pretty simple. What we're doing is we are building just a regular call, and then this .call is calling to a contract with an account ID of 42, 42, 42, 44, 42, so on and so forth. We're setting a gas limit of unlimited. That's what that 0 is there. And we are transferring a value of 10 from our calling contract to the contract we are calling to, the 42, the one that's the address of 42. And then we're actually setting up the input here. So the .execute input. And in this, we are we're calling a function on our other contract that has a selector bytes of flip. So we've defined these selector bytes in the other contract so that it's easier to find it and actually call it. And then we are pushing 3 arguments. So we expect that the flip function will take 3 arguments, a U8, a Boolean, and an array. And those are the 3 types we're pushing. And we also expect that it will return a Boolean. And then, of course, we'll actually just invoke it at the very bottom. And that is just kind of the high-level overview of cross-contract calling. Later in the presentation, I'll actually do a demo kind of showcasing how to actually do these cross-contract calls. And then also we will demo something else that Ayush will talk about in a little bit here. So I'll pass it over to Ayush to talk about custom environments.
Thanks, Vito. So whenever we work with the contract, we have the concept of environment. Frank mentioned about Frank gave a high level overview in the previous session. So we can think of environment as an education context for the contract. In the next slide, I will show you how it will look like. Yeah, so we like all aware that the substrate in substrate, like everything is generic and extensible, so we cannot make assumption as to what environment a smart contract is going to be executed. We don't know what actual block number is going to be. We don't know what user account type is going to be. The substrate does not define a specific types for a blockchain. It uses generic types throughout. The chains which are built on substrate can decide on their own which type they want to use. In terms of ink defines a trait environment, as you can see here, and also a default implementation of that trait, which is called default environment. As you can see here, there are the types that ink uses if no explicit steps are taken. So most substrate chains stay with this default substrate types, though, and ink just uses those by default as well. This default environment matches the default properties which are set out in substrate node template. As you can see here in the last line, chain extension is set as a no chain extension because the default environment assumes that uh, no chain extensions are present. Let me show in the next slide how we can compile using feature. So when we use the different environments, we need to change and recompile a contract for each target chain that uses a different environment. Changing the contract code in order to compile it for a different environment is quite annoying. Uh, we could introduce a cargo feature for our contract, as you can see here in the code base, which would allow us to select different environments when compiling using features. So suppose, like as you can see in the code for testnet, we have set up a custom environment, and for the other environment, we want to use the default environment. So when we will compile using cargo feature and just give the environment name, it will like compile accordingly. Uh, in the previous slide, I mentioned about chain extension. So let me give you a high level overview of chain extension before moving further. So yeah, yeah. In the default configuration of the pallet contract, a smart contract can only interact with the runtime via its well-defined set of basic smart contract interface. But in some scenarios, these basic set of features is not enough. So in that case, we use chain extension feature. So chain extension, basically, it is an API with which a parachain can expose certain parts of its business logic to smart contract developers. Through this, smart contract developers can utilize the business logic primitives of the chain to build a new application on top of it. So this is uh, just a high-level overview of chain extension. And Peter, at the end of the session, Peter will show this feature through a demo. Let me show you in the next slide how to configure the chain extension through the custom environment. Now, coming back to the custom environment, we need to set up the custom environment in order to use the chain extension, because in ink, contract needs to be configured like in order to learn about which types the chain uses. as you can see here, ink. There's an ink contract macro at the top of the code, which is an entry point for writing ink smart contract. To define a custom environment, like we have to pass a header attribute called env environment header attribute as shown in the code. So this tells the ink code generator which environment to use for the ink smart contract. The environment must implement the environment rate and provides all the necessary fundamental type definition for balance, account ID, etc. When using a custom environment implementation for a smart contract, all types that it exposes to the ink smart contract and the mirror type used in the runtime must be aligned with respect to scale encoding and semantics. Now, I'm handing over to Peter for the demo.
Yes, so hold on one second here. So we have, we're gonna do a demo here. And in this demo, it's kind of a cool use case. And we are actually going to take an ERC20 ink contract. We're gonna pass it through our swapper contract. And this is going to actually, using chain extensions, is going to swap this ERC20 with a squink coin that is in palette assets. So it's kind of, it's a contract. It's going to flip an ERC20 in the contract land with something that is in the substrate runtime land. So let me come back over here, and this we'll go ahead through we'll go through the demo first, and then we'll jump into the code and actually look at the contracts that we've used. So first thing is we have this squid ERC20, and this is an ink contract deployed to palette contracts. And then we have our squink coin. So this is a little ink coin right here that we will actually be swapping from. So this is substrate land, and then this is ink land. This is the contracts land. So first step, let's actually go ahead and deploy our swapper contract. So we'll go to add new contract, and we're in the contracts UI here. Upload new contract code. Let me just drag this over. So there we are. So here we go, swapper contract. And it's got quite a few things, quite a few functions here, because a lot of these are actually exposed from a chain extension that kind of bridges our palette assets with the ink contracts. And as you can see, it kind of has a similar interface to such like a ERC20 or a PSP22, where it's got things like transfer, it's got approve, and all of these are functions that we can then use to interact with our chain extension, which interacts with palette assets. Go ahead and press next, and everything will be successful. Upload and instantiate, perfect. So we've instantiated this contract, our swapper contract, and we can actually try to do a call here. So we're going to call from Alice, and we're going to try to do a swap. But first, we need to create the asset pair first. So what this is our squink coin has an asset ID of 1. So we'll go ahead and put that here. And we want to make the squink coin one-to-one swappable with our squid ERC20. So we will add that here. There we are. So this maps asset ID 1 over here, our squink coin, with our squid ERC20 contract that is already deployed. So go ahead and call that. Our asset pair has been created. And then let's see if we can actually do the swap. So we have this swap for asset function that allows us to swap the two things. So let's go ahead and set this up. Let's try to do 10,000. But you can see here that we get an ERC20 result and an error of insufficient allowance. The reason for this is actually coming from our ERC20 contract. And it's because our contract, our swapper contract, it doesn't have the privileges to transfer on behalf of Alice. This is something you might commonly see with like a decentralized exchange, where you need to actually approve the exchange to transfer tokens on behalf of your account. This is what we will do now. So we'll go over to our ERC20. Let's take our contract address here. And we need to approve that contract to spend tokens on behalf of Alice. So we will allow it to spend 10,000 tokens. So let's go ahead and call contract. And let's look real quick and just verify a couple of things. So the balance of Alice is a lot. It's 10x, right? There's a lot of zeros there. And the balance of our contract, our swapper contract, is currently 0. Okay, cool. So now we can actually do the call, except one step is missing still, where we need to provide, I guess you can call it liquidity of the Squink coin to our contract. So we need to transfer over some of that coin to our contract. So let's go ahead and just, let's keep it simple, and let's mint some of our Squink coin. And let's just mint a bunch into the contract, mint it, there we are. Okay, so now everything is actually ready to do. We've approved we've approved the contract to spend tokens on behalf of Alice. We've given Squink coin to our contract. We've minted it to our contract. And then the next steps are, we're actually going to swap some of our Squid ERC20 tokens with our Squink coin. So let's go to the command line here, and we are going to we're going to use cargo contract call to actually call this. So let's copy our address here, go to our terminal, and I'm going to paste in a command here. So there we are. So let's just walk through it step by step. So we've got cargo contract call from cargo contract. Our contract address is this one here. I just pasted this in. We are calling the swap for asset message, or a function within the contract. This is called from Alice, and we're passing two arguments. This first one is the asset ID, and the second one is how many tokens we are trying to transfer. Let's go ahead, press enter. Okay, something is failing. That's always fun. Let's see. Let's just see here if there's any errors it's given here. All right. Let's see why this isn't working. No. Okay. So something's going wrong here. Let's make sure assets were issued into our contract. And of course, everything always goes wrong on presentation day when we need to actually do the demo. All right. Maybe let's try to lower this down. Okay. So I'm not quite sure why it's failing. So let's try, maybe we can try to rebuild the contract and redeploy maybe. All right, so we rebuilt the contract, and we can try to deploy it here again, see if this works. I'll just run through this very quickly to see if we can actually get this working. Swapper v2, let's go ahead, next, instantiate, approve, contract. Okay, assets, mint. All right. Hopefully this actually works. If not, we may just need to go dive into the code. I promise it was working yesterday a lot of times, but let's see. All right. Still failed. Oh no. Okay. Asset pair not found. Oh, hold on a second. It's because we need to create the asset pair. Create asset pair 1, and we're going from our Squid ERC20. There we are. It's still failing. Oh no. Okay. Well, I guess let's not spend more time on that. Let's just dive into the code. Normally it works. I don't know what is going wrong today. But we've got 2 things here. So let's grab this one. So we'll first go to our actual substrate contracts node. And in this, we have, let me scroll up here. So in this chain extension here is actually providing the bridge between our pilot assets on the substrate runtime with our actual ink contract, the swapper contract. And it has, we can kind of see its interface right here. So it's built as an ERC20 interface, or PSP22 interface rather. And it's got, these common functions you normally see. So transfer from, approve, get the name, symbol, total supply, so on and so forth. And this basically exposes this interface is defined to be something familiar, like a PSP22 interface, to our contract. And it's got here some function IDs that we can use that will pass from our contract to the chain extension. So that way the chain extension knows how to route the call to the proper place. And we're using this implement try from as it's just a helper essentially to map our function ID to an enum here. So it's just easier to read, easier to follow. So we'll go down here. We're going to scroll to the bottom. And this is the actual entry point for our chain extension. So when the contract calls the chain extension, it's going to come here first. And within it, it's going to get this function ID. And this is the function that the contract is trying to call. So this is where that try from came from, where we'll take this function ID and we will kind of map it to an enum, and then we can match on that enum to find which function we should actually go to. So for example, if we go to a transfer, let's go ahead and take a look at that. So transfer, and here's the actual transfer function. So this is the function that when called by the contract will call pallet assets to actually perform a transfer for us. Very cool, because it's that bridge from contract land to substrate land. So we can come down here and we can actually see it's using pallet assets, and then we're transferring from our sender to this destination with the amount. And this is once again dispatched from a contract. And one thing to note here is this right here, this sender, we pull the caller from the environment. And the caller is actually the caller of the contract. So if Alice calls the contract, this will actually be Alice as well. So Alice from a contract can call the contract and interact with pallet assets through the contract on her account, which is very cool. However, for our use case of when we were trying to transfer or swap the squid token with assets that were deposited into the contract, we need to actually make this come from the contract. We need to call transfer for our contracts account. So transfer from our contract to whoever the calling account is. So we created a new one, transfer from contract. So we've extended out this interface a little bit, this PSP22 interface with this transfer from contract. And the only difference is we've changed from a .caller to .address. And this .address, it pulls, or it's the address of the contract that called the chain extension. So now when we call transfer, we are actually transferring from the contract to the whatever this input is for .2. And there's a lot to discuss in chain extensions, but for the purpose of this walkthrough, we won't go too deep. We'll just kind of show you the high level. Excuse me. And now let's actually look at the contract. So the first thing to note here is we have our chain extension right here, our chain extension interface. So these are all of the functions that are defined in the chain extension. So these are all of the ones we were looking at, token symbol, token decimals, transfer from. And note here, we are providing the function ID right here. So we've just, for the transfer from contract, the new one, we just kind of put a random one, short for dead beef. And these are the function IDs. So that way the chain extension knows where to route the calls to. And then we can scroll down, keep going. Here is our storage for our contract. And it's a pretty simple storage, nothing fancy going on. We have asset pairs, and it is a mapping from the asset ID of the asset and pallet assets with a reference to an already deployed contract. So in our case, this would have been the Squink coin with asset ID 1 mapping to our Squid ERC20 contract. Constructor, nothing fancy going on here. We are just calling default on it. So it just creates an empty mapping. And then the first step is to create the asset pair, which takes in the asset ID and the ERC20 address, or the ERC20, the reference to the ERC20 contract. And we just insert it into the mapping. But the swap for asset is where the cool stuff actually happens. So a user can call this function and pass in the asset ID and how much they're wanting to transfer. First step is we'll just go ahead and pull the ERC20 reference from our from our mapping, our asset pairs mapping here. So we're going to pull that out, and then we actually have this ERC20 reference that we can now use with the exact interface that's provided by the ERC20. So first step is we'll do this transfer from right here. And remember, it needs to be a transfer from because Alice is approving the contract to spend funds on behalf of Alice. And we're going to transfer from the caller. So if Alice is the caller, we're going to transfer from her account into our contracts account right here. So this means we're going to take the tokens from Alice, put it into our contract. If all of that is okay, we'll go ahead and continue. If not, we will panic the contract and just print out the result. Essentially, we'll panic with the message. So if you remember, we saw that insufficient allowance error in our contract UI. This line is what did that. And then here's where we actually call the chain extension. So this is where we're actually going from contract land into substrate land and calling palette assets. So it's environment, extension, and then we are doing transfer from contract. So this is transferring from the contracts account. We're going to transfer asset ID 1, our squink coin, into our calling the caller of the contract. So in this case, Alice. So we took coins from Alice here, and then we are giving coins to Alice right here. So it's just we're swapping them. And then if everything's good there, then we go ahead and everything is done, and it actually swaps those two assets. Now, so sorry this demo didn't work. That always happens on presentation day. The demos never work. But I hope this actually going through the code kind of gave you an idea of how this would work and why it's actually kind of cool, because we are using from Inc contracts, we're kind of interacting with the substrate runtime and swapping assets that are defined in different ways, one in palette assets and then one as an ERC20. Thank you so much for joining the call today.